Hello students, we are going to discuss bagging and random forest today. Now, in a nutshell, bagging and random forests are relatively similar in the sense that you are going to build a large collection of trees rather than doing only one decision tree that you've studied with me last week. We are going to discuss uh, how to build a collection of trees through these two concepts. So that's in a nutshell what we are going to discuss. And we will also study things that we call out of bag error, for example. And all these are going to be discussed in this lecture today. Bagging. In fact, bagging is also referred to as bootstrap aggregation. Now, the idea of bootstrap means that you are going to apply random sampling with replacement. I repeat, bootstrap means you are going to resample your data. When you're going to do your sampling, you're going to apply random sampling with replacement. And what is the idea behind? The idea is to reduce the variance of your decision tree. When you're applying a decision tree, if Mr. X applied a certain decision tree and predicted logged salary of the baseball players, as we discussed last time, Mr. X might be getting a result. If you do the same thing for Mr. Y, you would understand that Mr. Y would get probably a different result. It would not be surprising if the result differs a lot compared to Mr. X. Mr. Z will do the same thing. You would not be surprised if his result is also again very different from the others. Why? Because they are applying it, let's suppose, on different training sets. So what is happening here? This is why the decision tree is unstable in that sense, because it is highly it has high variation. And bootstrap aggregation or bagging allows us to reduce the variance of a decision tree. Now, in a nutshell, I just give you an idea of what it is. What is going to happen in bagging is that you are going to fit several decision trees. Why several decision trees? Because you will not have only one training set in the end, but you will have several training sets. How shall this be? I'm going to explain later on. But because you will have several training sets, you will have several results, obviously. For a regression setting, because you have different results, a different predicted result, what you would do is that you would do an average of all the results. For the case of classification, you will have a committee of trees which will cast a vote for a predicted class. Right? A committee of trees will cast a vote for a predicted class. Then what you need to do is to check which one has got the majority vote. And the one which has got the majority vote would be your final result in the end. So that's a little bit about what bagging is normally. Now, to understand the concept of bagging, we have to understand what is this idea of reducing variance. First of all, why by taking several random samples, you are going to come up with a reduction in variance. If we take a simple example to illustrate that, let's try to make an analogy with the concept of let's try to make an analogy with the concept of inference that you have been studying in other statistical courses. If you say that Z follows a certain normal distribution, let's suppose, or not Z, maybe I'll take another random variable, X follows a normal distribution with a certain mean mu and variance sigma squared. Let's assume it's like that. If our sample is large enough, now when I took X as normal, you should understand that it's not necessary for me to have X follows a normal. It could be any distribution, all right? I'm just taking that by convenience here. Now, if you consider X bar means what? An average of X, and you look at the distribution of X bar, you generally know that it will follow a normal with the same mean mu, but The only difference is that the variance now is not sigma squared, but it is sigma squared over n. So you already see what's going on. In the context of one decision tree, you are expected to get a certain variance, but in the context of several decision trees where you are taking an average, your variance will not be the same as it was before, but it is supposed to be decreased. If you just look at it in the concept of central limit theorem, it's not necessarily central limit theorem. It's just that if you have the expected value of, if you have a variance of x, is equal to sigma squared, we all know that the variance of x bar would be equal to sigma squared over n. So this is why we are talking about the concept of averaging a set of observations, which is expected to reduce your variance, because look at what happens. Sigma squared will be divided by n compared to sigma squared. So the variation will decrease normally. So we can make this analogy to understand this principle of averaging. All right. So how is bagging supposed to be applied? I repeat, supposed to be applied. Let's have a look. Sorry, not how bagging is supposed to be applied, but how is this concept of averaging sets of observation supposed to be applied? I'm not referring to bagging here. I'm referring to how this concept of averaging set of observation is supposed to be applied. It's going to be applied when you have several training sets. And then from these several training sets, you will have several prediction results from your model, from your decision tree. And then in the end, you will do an average of all the predicted results from these different training sets. All right. So that is the overall idea, which can be summarized in the next slide as this. You will apply the decision tree to estimate your output, all right, through your feature space X, and then this is going to be applied for one tree, this is going to be applied for second tree onwards up to the BF tree. That is depending on how many training sets you've got. So the B represent the number of training sets that you're going to have, and the idea is to do an average of all the different results that you get from each tree, and this is what you are supposed to have. But you have to understand something. When we are referring to several training sets, it would not be practical to have different training set. It is not practical to have multiple training sets. In reality, we can't really have multiple training sets. All right. So this is why we come up to the concept of bagging, where the idea is to take bootstrap samples. All right. Is to apply bootstrapping. Bootstrapping allows you to repeat samples. All right. To repeat your samples. That is, there is to have repeated samples, that is, you can sample with replacement. So in the same training, you have a training set that you have. What is going to happen? You will sample within it, and then the next time you will sample again with the same observations got back into the pool. So in this regard, when you are taking what we call repeated sample, that is sampling with replacement, you have a possibility of having several training sets in the end. So this is where we come up with the same idea as we said, but the only difference is that instead of having multiple training sets, we will have bootstrapped training sets. So this is where bagging comes in. It is, instead of considering several different training sets which are not practical, what we do is that we consider a bootstrap training set. All right. In the same training set, you are going to have a random sample. You are going to have a random sample of your data within you are going to have a random sample of your data within the data set. You will have a training set that will be obtained. Then when you have obtained this training set, these records are sent back into the pool, and you repeat this procedure. You get a different training set from the overall data. You get a different training set from the overall data, and this will be repeated different times. So that is the idea behind bootstrap training data sets, like bootstrap behind bagging. And then obviously the same idea is that you are going to do an average of all the different results that you get from the different trees that have been fitted from the different bootstrap training data sets. So that's a little bit what bagging is about. One thing to be noted here is that when you are growing these different trees on the bootstrap training sets, these trees are meant to grow deep and are not pruned, right? They are not being pruned normally, these trees. Then, of course, based on what I explained to you earlier, these trees are supposed to reduce the variance, all right? And for the concept of classification problem, we can come up with the idea of taking a majority vote, right? Which I explained to you a little bit earlier, but the majority vote refers to the overall prediction in the most commonly occurring majority class among the B predictions, right? So we just need to have a look at, because each tree, let's suppose you have tree 1, you have tree 1, you have tree 2, tree 3, and so on. Each of these three, based on a certain region, they will be producing a predicted class. They will predict a certain class for a certain region, all right, of the data. For a certain partition of the data, they will predict a certain class. I suppose you are talking about good credit risk, bad credit risk. You get good, you get for the same region, you get good, and it goes on like that. You get good, and each time it is predicting good, but then for a particular region, let's suppose you get bad. Okay, so you would understand that now for the same region, for a particular tree, for the same region, you are getting something bad now. You would understand that if you continue this process, you will need to have a look at which one is the majority among all these. Which one is a majority? Which one comes more frequently? Which predicted class comes more frequently? All right. This is what you are going to take as final result. All right. The overall prediction is going to be the one which is most commonly occurring among the majority class. You will have this also refers to the majority class for a particular region. This refers to majority class for a particular region within that tree, and so on. So you just need to look at which one appears more often, and the one which appears more often obviously wins it. All right. Now, how do you decide on the number of bootstrap sample? You see, uh, normally when you when you are applying bagging, you should not worry too much about whether you are taking a too large value of B and think that this has something to do with overfitting. It has nothing to do with overfitting, because just remember something. Overfitting is related to the amount of split variable and split variable that has been selected in your decision tree. The more terminal nodes, the more split point you have, then you will obviously have overfitting. But in the context of bagging, B has nothing to do with overfitting because it's just building a tree. All right. It is all about building trees. So whether you are having a large value of B or small has nothing to do with overfitting, because it is not going to make more split variable or it will not increase the split variable. So it is just increasing the number of trees that you want. So generally we take a sufficiently large value, right? A generally sufficiently large value has been selected. Why? Because when you take a sufficiently large values, what happens is that the errors will generally settle down at when you take a large value of B. And what I mean by that is generally you will have results that tend to converge to when you take a sufficiently large number of bootstrapped sample. So the idea is to take a large value as far as possible. But remember, the more that if you are taking too large value of B, you will not have any, you will have to understand that it will be more computationally intensive. You would, it will be a cost on the computational side, but you won't be getting any improved result in the end. So ensure that when we are talking about sufficiently large, it's not too large up to the point of having your computer to wait for a very long time before you get the results, obviously. Now, when we come to the concept of bagging, we have to understand that we need to find a way of evaluating the different errors that we get. Okay, we need to find a way of evaluating the errors. It's going to be a little bit different from what we have done before. What happens is, on average, each bag tree will be using about two-thirds of the observations. That's what it does on average, right? It uses about two-thirds of the observations. The remaining one-third now of the observation which is not used to fit the tree, is what we refer to as the out-of-bag observation, right? The remaining one-third which has not been used to train the model, to train the bag tree, is what we refer to as the out-of-bag observations. What we can do is we can predict the response for a certain observation. All right, we can predict the response for a certain observation, let's suppose I here, using each of the trees in which that observation was out of bag. So when you are fitting the tree, understand that each time that this observation was not taken was not run, was not used to run the model, each time, suppose we are talking about observation 1, if you have been applying 10 times, all right, what the idea is about is normally you need to have a look at this observation, how many times if it has not been used, all right, to train the model. And the number of times it has not been used to train the model would refer to the number of times that it has become what we call an out-of-bag observation, all right? This is what we refer to out-of-bag observations here. If the decision tree has been run 10 times, let's suppose 7 times this observation has been used for the training. Obviously, if it has been used for the training, other observations would be out of bag. But let's suppose 3 times this observation has not been used for the training. If this observation has not been used for the training 3 times, all right, let's suppose we refer to it as tree 1, tree 2, and tree 3, where this particular observation has not been used as training. So you would refer to it as an out of bag observation. This is going to be another out of bag observation 2, and out of bag observation 3. Out of bag observation 3. All right. So now what is going to happen is that we are going to have a look at the prediction that we get from when we have run the tree over all the observations. When we've run the tree over all the observations, this one is out of bag. So what we just need to do is to check the result that we get on that out of bag through the training set. All right. We just check the result that we get on the out of bag through the training set that was applied for that tree to be out of bag. And we are going to repeat this again. We are going to apply that decision tree on that with that training set on that out of bag error. We are going to apply this decision tree that has been applied here on that training set on the out of bag error. That is, we are going to do the prediction on this out of bag error, and then we just need to do an average of these out of bag errors that we got. So this is the principle that I explained here. So normally, if you have been training the model, if two-thirds of the data is going to be used for the training, there would be around one-third of the predictions which will be left out. Okay, around one-third of the observations will be generally used for prediction. And for the context of regression, what we do is we are going to take the average of these errors, all right? For the context of classification, we are going to take the majority vote, as I explained to you earlier. So I repeat just quickly for you to understand is that when the tree has been built 10 times, if that particular observation, the first observation, was considered over 7 trees, that for 7 trees that you have built, that you have been applying, this observation was in there, you don't worry about them. But what you look at is the 3 times, because as I said to you, about 1/3 of the observation will be used for prediction, right? Because about 1/3 of the observation will be out of bag. So if you look at this particular observation 3 times, let's suppose it has not been used for the training. Other observations have been used for the training, all right? So, but this one, let's suppose it has not been used, then it becomes an out of bag observation for that particular tree that was built there. And it becomes an out of bag observation for that particular tree, an out of bag observation for that particular tree. Okay? So each time that it has become out of bag, what you do is that you are going to predict the results that you get. You're going to predict the results that you get from that tree that was built here. On this out of bag, you are going to predict the result that you get from that tree here on this out of bag, and that tree here on this out of bag error, on this out of bag observation. And then in the end, what you do is you do an average of all these prediction errors that you will get, all right? And this is what we will refer to out of bag error estimation, right? So we will get a single out of bag error prediction for the IF observation. And you have to understand that this process has to be repeated for the second observations and so on and so on, okay? So this is a little bit about out of bag error. It's a bit similar to the idea of testing set, but here it's not going to be like the testing set because you are taking several decision trees. This is why we have a concept of out of bag error. So when we are referring to the error here for the case of regression, we are referring to the mean squared error, for example. And for the context of classification, we are referring to the misclassification error rate, for example. Okay. So this is a little bit about out of bag error estimation. Now we are going to move on to the concept of variable importance. You see, when you are applying bagging, you have to understand that we are running several decision trees. It can be 100 decision trees, it can be 500 decision trees, I don't know. But understand that if you have 100 decision trees, it becomes a big issue for interpretation. You cannot imagine that it would be easy for you to interpret 100 decision trees. All right. So you have a problem here. Normally, the advantage of using bagging is that it improves your prediction error. That's one of the things that is going to happen. But in the end, the other the limitation that we have from this method is that you will not be able to come up to an interpretation of a decision tree. A decision tree is easy to interpret. We all know it. But in the context of bagging, how can we interpret the 100 decision trees? It becomes an issue. All right. So for prediction accuracy, it's going to be improved using bagging. But in terms of interpretability, it's not going to be the case. All right. It's not going to be the case. That's one of the issues that we have with bagging. What happens is that normally you will have difficulty in determining which variable is more important to the procedure. You don't have an idea about which variable is important. In the context of a decision tree, you get the idea, all right? But in the context of bagging, you will not know because you are dealing with 100 decision trees. So it's not possible. So then you need to find a way of determining which variable is important. All right. So remember, one of the things that you need to understand is that in bagging, the prediction accuracy is going to be better than the decision tree generally, but at the expense of interpretability. Uh, Despite this issue of interpretation, we can try to come up with an overall summary of the importance of each predictor. Each predictor means each uh, variable in your feature space using the residual sum of squares, all right, for the context of regression tree, or for the context of classification tree, we would refer to the Gini index, for example. So we can use these two measures to come up to an overall summary of the importance of a certain variable. To do so, we can have a look at a certain split, all right? We can have a look at a split of a given predictor. And we look at the total amount that the RSS, that is the residual sum of squares, has been decreased due to that split, all right? And we basically need to have a look at the average of these residual sum of squared errors over the different trees that have been built with a specific split and see how much it has decreased. So we just need to have a look at the total amount that the RSS is decreased due to the split over a given predictor in the context of bagging. Okay. Now, similarly, in the context of bagging for classification tree, what we generally we will do is that we can add up the total amount that the Gini index is decreased by splits over a given predictor, average over all the B trees, obviously. A large value indicate an important predictor because it means that if the uh, residual sum of squares is decreasing a lot for that particular split, it means that this for that particular split over that given predictor, it means that this predictor has a great impact on your result. We can normally, to make this easier, we can represent it in a graph, all right, to understand what's going on. Uh, if, for example, you have a look at this one, okay, you can obtain a graph of the variable importance. We just need to look at the mean decrease in Gini index for a variable, if it is, of course, categorical, and if it is quantitative, we need to have a look at the mean decrease in the residual sum of squared errors. All right. And as you will see here, the one which has the greatest mean decrease is TAL. If this is this variable importance measure refers to the mean decrease in Gini index, right? The one which has the greatest mean decrease in Gini index is the one that is going to be the most important variable. But it depends on graphics. Sometimes it depends on software. Sometimes some software will give um, the greatest decrease on top, and then it goes in decreasing order. But this one is giving you the result uh, in rather from smallest decrease to um, going downwards to the highest decrease, right? But it's not always the case. It depends on the software what has been given to you. So in the end, just look at the mean decrease in Gini index, or just look at the mean decrease in the residual sum of squares. Here you get an example of the variable importance. This is the most important one, and it goes on like this. So we are going to now discuss on the random forest. Random forest. In fact, bagging and random forest, they are similar in many ways, but still there is one major difference between these two methods. The major difference is in the choice of your predictor variables. In bagging, what happens is that you consider all the p predictor variables that you have. if you take, for example, the case of the eaters data, if you take, for example, the case of the eaters data, there were about 20 variables in your feature space, if I'm not mistaken. And then in the context of bagging, you would take all the p variables and run the bagging uh, algorithm. But in the context of random forest, the difference lies in the fact that you are not going to take all the 20 variables, but you are going to take a subset of these 20 variables. You are going to take a subset of them, maybe 10, maybe 5, things like that. For each decision tree that is going to be built, we are going to take a subset of these, a random subset of these variable. Now, what is the idea behind this, taking a random subset? The idea is to come up with decorrelated trees. When you look at bagging, what is going to happen in bagging? If in bagging, just as in random forest, you are still working with bootstrapped samples, as I explained to you when I explained bagging. But when you are applying bagging, if there is a very strong predictor, if there is a very strong predictor, let's suppose it's the number of hits in 1986 was one of the strongest predictor that you have. You would understand that for all the trees that will be built, depending on how many trees you are going to build. I suppose you want to build 100 trees. You might not be surprised if for all the 100 trees that are going to be built, each time it will come first as will appear as the first split. It will not be surprising. So then, if this is going to be the case, what is going to happen is that each and every time the results might be correlated among themselves because of this strong predictor that you have in your data set. So each time you might have a results that are going to be correlated. Indeed, it's going to reduce variance, but not that much. Okay, such using bagging, you will come up with a reduction in variance, but not that much. But the best would be to consider decorrelated trees. All right, and this is why in the context of random forest, you are not going to take each time each tree that is going to build, you are not going to take all the 20 variables each time, because what's going to happen is that each time it will give you the same split that comes first if ever that variable is very strong. So in the random forest, what it will do is that it will take each time a random sample of your predictors, a random sample M of predictors from your 20 predictors. Let's suppose the random sample is 5. So each time that the tree is going to be built, it's going to take 5 variables and run the decision tree. And then the next time it's going to use another 5 variable and run the decision tree. And each time it's going to use a different random sample. Of course, sometimes there would be similarities between the different trees, but most of the time what is going to happen is that by applying this principle, you are ensuring that the strongest predictor does not come first each and every time. Hence the idea of decorrelated trees. So there is an advantage by applying decorrelated trees is that when you're applying decorrelated trees, you are going to reduce the variance even more than if you were to apply bagging. So that's a little bit the idea behind random forest. The next question that arises is how do you decide on this value of m? Now, generally, what happens is that in a classification problem, the typical choice for m would be the root of p. If you have 9 variables, so if you had 9 predictor variables, what happens is that m would be chosen to be free. So each time it's going to run the decision tree on three variables in your feature space, which has been selected randomly. So each time it's going to do that on three, which are not going to be the same three variable each time, obviously. It's going to change. In the context of a regression problem, it's going to be 9 divided by 3. In our context, it's going to be the same, but it's going to be 9. It's going to be p divided by 3. So that's a little bit the typical choice of uh, the typical choice that we would go for if in case we want to apply a random forest for either a classification problem or a regression problem. Okay, remember that by applying a random forest, what happens is that the algorithm does not even allowed to is not even allowed to consider a majority of available predictors. It's going to consider only a subset of these available predictors. And the idea is to come up with decorrelated trees, as I explained to you earlier. So here the slide is referring a little bit to what I explained to you earlier, is that if you have a strong predictor, each time what's going to happen is that the bag trees will come up with more or less correlated results. All right. So which is not necessarily a good thing. This is why we want the variance to decrease even more, and for the variance to decrease even more, we want the trees to be uncorrelated, to be decorrelated. All right, and this is why we apply random forest. As I explained to you again earlier, is that bagging will not lead to a substantial reduction in deviance, although it will do, but compared to a decision tree, a single tree, but it won't do that much compared to what a random forest will do. And so that's one of the advantages of the random forest, in fact. Uh, the advantage is that um, averaging many the advantage that random forest has over bagging is that when you average many in bagging rather, when you're averaging many correlated quantities, that does not lead to as large of a reduction in variance as averaging many uncorrelated quantities. When you're averaging many uncorrelated quantities, you come up with generally a larger reduction in deviance. So this is why the random forest has got an advantage over bagging in that sense. So again here, it's a little bit similar to what I've been explaining to you earlier, is that not all of the predictors will be considered, all right, which means that when not all of the predictors will be considered, every variable in the data set will have an opportunity to have a say the in the result, all right. Every variable in the data set will have an opportunity to have a say in the result. So as we said, random forest is about decorrelating the trees mainly to come up with a more reliable result. Now, again, as I told you, the main difference is in the choice of predictor variables. In bagging, all the predictor variables are considered, all the P predictor variables are being considered, which give you the same the same split most of the time, especially if you have a strong uh, predictor variable, but random forest takes a subset M of that P, all right? And I just explained to you how we come up with that selection of M. Using a small value of M in building a random forest will typically be helpful when we have a large number of correlated predictors. Just remember that. So here we will see, for example, the choice of M. When M is equal to P, you have a yellow line. You see the classification error rate. For the yellow line here, represent bagging, okay, because you are considering all the predictor variables. However, these two lines, the green one and the black and the blue line here, They are they are basically a random forest procedure which has been applied. And when P is when P divide by, when you're using P divided by 2 for the case of a classification problem, you will see that the test error is generally relatively high and even higher than bagging. But when M is taken as a root of P, the the test error, the classification error rate goes even lower. This refers to what I explained to you earlier. That is, for classification problem, M is generally taken to be the root of P. And for regression problem, we generally take it to be P by 3. So, having understood the main difference between these two concepts, remember that just one thing I wanted to remind you is that random forest, the principle that you have learnt in bagging, is the same principle that applies to a random forest. Okay, it's the same principle that applies to random forest. Uh, these principles that we studied in terms of, for example, the bagging is based on bootstrap sample. Random forest as well is still based on bootstrap sample. So there is a lot of similarities. The only difference is about the choice of M. So in what we are going to do this week is in the class we are going to apply the bagging, and we are going to apply random forest on the car seats data which is available in the ISLR package. So that's going to be what we're going to do next. So that's a little bit all that I wanted to talk about for random forest.